Welcome all of you. Since the last class, we have been discussing about polarization transfer technique to enhance the signal intensity of dilute spins. And we took the example of, for example, homonuclear case and also heteronuclear case. And there are two ways to do the polarization transfer. One is called selective population saturation, other is selective population inversion. Both are possible. We saw that. When we try to do the selective population transfer also, we saturate one of the transitions and we saw the gain in the intensity of its coupled partner. Both the peaks there was a gain in intensity. In the case of inversion also it happened, but selective population inversion has a better intensity. Same thing we saw that in the heteronuclear case. We took the example of carbon coupled to proton. Carbon has a gyromagnetic ratio of 4 times smaller than that of proton. Accordingly, we took out the populations, calculated, worked out with the population such that we get the intensity of protons 4 times larger than that of the carbon. Then we saw what happens for selective population transfer and selective population inversion, both of them. And we saw in selective population inversion, we are going to get the signal intensity gain of -3 and +5. We get gain in intensity, but there is antiphase character for that. How do you overcome this? If you do the decoupling, because we need to do the carbon-13 decoupling to detect the signal. If you do the decoupling by going into antiphase character signal, we get nullified. Whatever the gain we get is going to be lost. To overcome this problem, an idea is to put a delay after the detection pulse for another 1 over 2j. Then we saw the signal, which were antiphase in character will get, will become in phase character. Both alpha and beta components or doublet components of the carbon-13 doublet will become in phase. Instead of -3 +5, they will become +3 and +5. Now we do the decoupling, we get gain in the signal intensity. This is a fantastic way. It is called a polarization transfer technique. This is what we will continue with this further today. And in the polarization transfer technique, there are two ways to do that. How do you transfer the polarization? One is by doing nuclear over-Raser effect, which I am going to discuss in one of these classes, subsequent classes. And other is what is called a coherence transfer. Coherence transfer is called Inept. What is Inept? We will explain that later. Now in the sensitive enhancement technique, we will try to understand. One is we will go for NOE, which is generally done through what is called through space transfer. There is no spins need not be J coupled for it. For NOE transfer, spins need not be J coupled. What is required is a spatial proximity. As long as they are close in space, preferably less than 5 angstroms, then if you hit one of the protons or one of the spins, other spin gets, there is a transfer of magnetization to other spin. It could be more or less, that is a different question. But there is a transfer of magnetization without J coupling, without chemical bond. It is a direct through space transfer. We will discuss that later. And here the efficiency depends upon 1 over Rij cube, 6th power of the distance between two interacting spins or two spins. And it is very large, because 1 over Rij to the power of 6, small variation in the R, because it is power of 6 and there is going to be enormous change in the intensity. So this is the important concept. So NOE is a distance dependent, and small change in the distance will affect the NOE intensity or gain in NOE to a large extent. That will come later. Next part is Inept. Inept is what we are going to discuss today. This is called insensitive nuclei enhancement by polarization transfer. That is called Inept. Inept transfer always occurs through J coupling. Remember, I told you in the NOE, no need of J coupling. Spatial proximity is the requirement. For Inept, J coupling is important, and it happens only through J coupling. And Inept can be done by any two J coupled partners. It need not be only heteronuclear spin. For example, it could be 2 protons and adjacent carbons. That is, if there is a vicinal coupling, when there are 2 protons on the same carbon, or adjacent carbons, that's also possible. And proton, it is directly bonded carbon, one bond heteronuclear coupling, that's also possible. A proton and the carbon next to its own carbon, two bond heteronuclear coupling, varieties of possibilities we can think of, vicinal, two bond coupling, three bond coupling, all those, one bond heteronuclear coupling, everywhere you can do that. So this is a very important concept, the polarization transfer. Where do you use it? We use this polarization transfer. I already discussed an experiment called DEPT, distortionless enhancement by polarization transfer. When I discussed carbon 13 spectra, and I showed by doing this DEPT experiment, 3 experiments 45, 90 and 135, I showed we can distinguish between CH carbon, CH2 carbon, CH3 carbons. At that time I did not explain polarization transfer for you, because the carbon 13 I was discussing, before that it was not introduced. Now you have understood what is a polarization transfer. So this is one of the experiment is, in the DEPT experiment, not only you could identify the different carbons attached to different protons, there is a gain in the intensity because there is a polarization transfer in that experiment. Distortionless enhancement by polarization transfer. That's why DEPT is an experiment which you have to always use. Previously we used APT, attached proton test. APT doesn't mean there is a polarization transfer there. It is only a proton test. Here it is a polarization transfer in DEPT. So DEPT experiment also identifies different carbons attached to different protons, but here there is a gain in the intensity. Better advantages compared to APT. And I showed already several examples of how we can utilize a DEPT, when we discuss carbon 13. But only thing is, if there is a polarization transfer, you please remember that we have already discussed now. And also it is used in number of 2D experiments like HSQC and HMBC etc. to gain the intensity of the dilute spins. Enhance the signal intensity of the dilute spin, we use this one. There are 2 important consequences of Inept. One is sensitivity to the dilute spins is enhanced because of polarization transfer from abundant spin to rare spins. There is a gain in sensitivity, we saw that. There is 4 times gain for proton and carbon, and this is given by the ratio of gammas. If you go to nitrogen 15, 10 times. Okay. Now secondly, the repetitive time for signal averaging is 5 times T1 instead of 5 times carbon. Carbon T1 is always larger than proton T1 usually. It means we can use proton 5 times T1 means it will save the experimental time for me, because the repetitive time is now 5 times T1 not instead of 5 times carbon 13 T1. As a consequence, there is enormous saving in the experimental time when I do Inept. Not only gain in intensity, there is also saving in the time. Now how does Inept works? We will understand that. Of course we know polarization transfer, so far we have understood. Same thing, but how we do in experimentally in a different, we will discuss that. All depends upon delay and application of 90 pulse, 180 pulse. That's all we have been discussing this in the spin echoes. Exactly like spin echo, but we will see now how the polarization transfer takes place. Apply a 90-degree pulse to create coherence. Coherence means bringing the magnetization to x axis or y axis. Then wait for a period 1 over j. After 1 over j, the components of the doublets are opposite in phase, antiphase doublet. Okay. Okay. I'm sorry, not 1 over, it is 1 over 2j. I'm sorry, it is not 1 over j here, it is 1 over 2j. Okay. Because antiphase doublet is 1 over 2j. 1 over j again they will come back and refocus. That was a typo mistake. So now we will understand how it works. Apply 90-degree pulse on the proton channel and wait for a period 1 over 2j. There is an antiphase character for proton. Correct? That's what we have understood. So you apply the 90 pulse, whichever the axis you apply according to the right hand thumb rule to find out where the magnetization comes. If you apply a 90-degree, let us say a pulse along this axis, magnetization is along the z axis, it will come to this axis and then they will start moving by 90-degree at exactly 1 over 2j in the xy plane. Fine. Now this is for proton. Selectively we are applying pulse on proton. This is the beauty of NMR. You can selectively apply pulse on any one of the nuclear spins. What about carbon 13? We are not touching it. We are not even applying any pulse on carbon 13. That means there is no coherence in the xy plane. As a consequence, you will not get any signal. Now we do the Fourier transformation. Here you are going to get a signal, antiphase character, true, one is positive, other is negative, that is fine. Here there is no coherence at all, absolutely no spectrum at all. This is just after 90 pulse, how the signal will be seen for proton and carbon. Apply 90 pulse, wait for 1 hour 2J, you will have an antiphase character signal for proton and no signal for carbon. That is the concept you have to understand. Now another thing we will do is, we can apply 90 pulses simultaneously on both the J coupled nuclei. For inept, important concept I told you is the spin should be J coupled. We apply 90 pulses simultaneously on both the J coupled spins. Very interesting thing happens. When you apply 90 pulses simultaneously, the coherence will jump from one nucleus to the other. Instead of applying to only one of them, we apply simultaneously. The coherence from X or the proton will jump to carbon 13 nucleus. It is very interesting thing is going to happen. With simultaneous 90 pulses for a J coupled spin, this is what happens. First we had antiphase character for proton and no spectrum for carbon 13. Apply 90-degree pulse. This is for proton and this is for carbon 13. Now what is going to happen 90-degree pulse when you apply? There is no coherence here, whereas carbon 13 will have antiphase coherence. Simultaneously applying 90 pulse on both. What is happening? The coherence of proton is transferred to coherence of carbon 13. Do the Fourier transformation. You have no spectrum in the started nuclei, but there is a signal in the transferred nuclei. From proton we transfer the magnetization to carbon 13 and this become antiphase character. We started with proton which is antiphase. There was no signal for carbon 13. Apply simultaneously 90 pulse on both of them and do the Fourier transformation. Now there is no signal on proton, but there is antiphase signal doublet on carbon 13. This is a very interesting thing happens. This is what is called jump of coherence. Coherence is going to be jumped from one nucleus to other nuclear spin. With two simultaneous 90 pulses, antiphase coherence is transferred. So there is no coherence on the starting spin, only on the end spin, transferred spin. So simplest inept sequence. How does inept sequence works? The simplest of it is like this: 1890, 1 hour 2J, 290 pulses. This all we have been understanding for quite some time. After apply 90-degree pulse, after 1 hour 2J, there is antiphase character. That is what doublet component moves apart by 90 degree, both of them. One will move fast moving, slow moving, both move by 90 degree, became antiphase in character. That we have been understanding for quite some time. Just now I showed you already, we applied simultaneously 90 pulse on both of them. Then what is going to happen? The coherence will transfer from proton to carbon 13. And this coherence transfer is possible only if they are J coupled. That is what I have been telling you. This is simplest of the coherence inept sequence. All I said is we have to have antiphase character to be created and apply simultaneous 90-degree pulses to transfer to the other spin. That is what we have to do, and we did this. But what happened again? Carbon 13 is antiphase. Again is a problem for us. See, after 90 pulse, both the proton vectors will be coming like this, and then carbon 13 is not touched at all, it is still on the Z axis. Give after 1 hour 2J, this proton will start exactly after 1 hour 2J, both the vectors move by 90 degree, became antiphase in character. But here what is happening? Carbon 13, still I am not touching, I have not even applied a pulse on that. Now what I will do is, I will apply pulse on proton and also on carbon 13, simultaneously 90% both of them. What happened? This antiphase which was here moved here. This is a diagrammatically I am telling you what is happening for the magnetization after 1 hour 2J and after simultaneously application of both the 90 pulses on both proton and carbon 13. All the carbons may not be on resonance. This is I think what happens. Okay. But this should happen in such a way, we have different chemical shifts for different carbons. They are all having different offsets. They not be at the same chemical shift. Then what will happen? There is they will evolve as per the different chemical shift. There will be a phase distortion. They will be moving with different frequency, different phases. They start processing, in the XY plane, because they are all not at the same. If it was like I told you in the case of spin echo, quaternary carbon, there is no precision. It will be always along the x-axis. It locked along that. Whereas with the J coupled, fast moving, slow moving, will be moving. If different carbons have different chemical shift, they will be moving with different frequency, different phases will be there. So there will be phase distortion, because all of them may not be having, may not be in the on resonance because of different chemical shifts. Then how do you overcome this different chemical shifts? How do you overcome this evolution of chemical shift leading to phase distortions? We already understood this, please remember. How do you do the refocusing of chemical shifts? Do spin echo. When you do the spin echo, then what is going to happen? You refocus the chemical shifts, apply 180 pulse at the center, create a spin echo sequence. Then a chemical shift evolution can be stopped, and then we will be refocusing. That is one way. So what we do is put a 180 degree pulse in the middle of the 1 hour 2J period. Up to at 1 hour 2J, they will become antiphase. In the middle of that 1 hour 2J, apply 180 pulse. Then it will refocus chemical shift of protons. Exactly what we do. So another thing what will happen, there may be evolution of J coupling also during that period. How do you prevent that? How do you refocus J coupling? I told you already. You have to prevent the J evolution, put 180 pulse on carbon 13 also. Okay. Simultaneously if you put on that, then J would be refocused. So inept sequence with chemical shift refocusing is the experimental sequence, is like this. What is the experimental sequence? This was the sequence. Okay, in the case of proton, earlier 90, 180 was there. In between you have put 180 exactly at 1 hour 2J. This is the total delay is 1 hour 2J. But what we did is, at the center we have put a 180 pulse for refocusing chemical shifts. But now we are applying 180 pulse also to take care of J coupling, JCH, carbon proton J coupling. Then simultaneously apply 90 pulse on both of them, transfer the coherence from proton to carbon, start collecting the signal. That is exactly what we are doing. This is inept sequence. So how does the magnetization evolves? During the inept sequence, we can understand by a vector diagram. I will show you using the vectors how magnetization is going to evolve during this. The different time periods of pulse sequence in the inept sequence we label by an alphabet A, B, C, D, E, and each stage of the pulse sequence at different stages of A, B, C, D, E, what is happening to the spin vectors will diagrammatically will visualize. We can try to understand diagrammatically. This is the pulse sequence, and this beginning of the pulse is A, then 90 pulse is B, then evolution C, D, E and F. We have put 6 different time periods, points. This is a spin echo sequence, we apply 180. Of course, you all know what happened to the magnetization at A. Nothing is being done. If you wait for a long time, the spins would have attained thermal equilibrium. That is well known. Apply 90 pulse, what will happen here? Immediately there is a phase coherence, you bring all the magnetization to one axis. You will flip by 90 degree. That is what happens. Proton is the doublet due to coupling with carbon 13, and HA and HB are the doublet components. At A, both these components of the doublet are along Z axis and is in equilibrium. because we are not even disturbed. It completely spins have relaxed, and they are in thermal equilibrium at along z axis. Both alpha and beta components of the proton. Why alpha and beta is coming? H alpha is coming because of C alpha, H beta is coming because of C beta, because of coupling. Alright, this is the diagram. At point A in the pulse sequence, both the vectors alpha and beta vectors of proton are along z axis. We will keep it like that. Continue further. Apply one at B after 180 pulse. HB and H alpha and H beta components of magnetization are flipped to y axis by 90 pulse. I am applying a x pulse, so I am flipping to y axis. All x, y, z are orthogonal to each other. That you know that. Okay, I am just simply telling x, y axis. It has moved to y axis. Both alpha and beta components are there. That is the situation at point B. That is correct. No, it is very clear for you. Both which are here I have brought down to x axis or y axis. What is happening now? We are allowing it to give for move for 1/4 of j. In our equation theta is equal to how much it is moving? Pi into Td into 1 over JCH. If you JCH you multiply by that. So now Td is 1 over j. Pi into 1 over 4j into JCH is pi by 4. What is pi by 4? 45 degrees. So what is happening is at C you use that equation theta is equal to pi into Td into JCH. So Td is 1 over 4j, jj cancel out is 1 over 4. So pi by 4 it is 45 degree. So alpha and beta components at the point C will be, they would have moved by 45 degree. One is a fast moving component, other is a slow moving component. This how it is. One moves like this, other moves like this. Okay, alpha and beta components have rotated by 45 degrees at exactly 1 over 4. So this is the situation at point C. Okay, we will continue further. At point C, another thing what is happening is immediately at that point we apply a 180 pulse on proton. We will worry about carbon 30 later. What does 180 pulse on proton will do? It will invert the populations. Alpha and beta components get inverted. What will happen? Alpha will become beta, beta will become alpha. They get inverted. But they continue to rotate in the same direction. They have inverted, applying a pi pulse. Then what will happen? We are applying a pi pulse along x. So here you rotate like this. When you rotate like this, the vectors which are here come to this direction. And they were moving like this, they continue to move in the same direction. So at D, now we are applying simultaneously pi pulse on carbon 13 also. So 180 pulse on proton inverted the alpha and beta components of proton. But we are also applying carbon 13. What does it will do? Remember, carbon 13 is still in the z axis. We have not touched it. We have not applied pulse on carbon 13. Look at this sequence here. Now only we are applying 180 pulse. Till now we have not even touched the carbon 13 spin. Then what it will do? It will change the magnetization from plus z to minus z. They were at thermal equilibrium. Carbon spins are at thermal equilibrium along plus z. Now come to minus z with 190 pulse. Okay. The population beat levels between transition 1, 3 and also on between 2 and 4 are inverted because of carbon 13. That is what we did. So this is what happens. Before 180 pulse, this is the population difference which we saw for calculation of the polarization transfer. We just took the example. This is before 180 pulse on carbon 13. Now 180 pulse on carbon 13, what is happening? See here, these spins have been moved here and this here. So what is happening is the inversion has taken place. Spins from this state 2 it has gone to 4. Spins which were in 1 came to 2 exactly. So the population inversion has taken place for carbon 13, which was along Z. So H alpha component, how it was coming? It was coming because of C alpha. And HB was coming because of C beta. Now what is going to happen? H alpha, which was coming of C alpha, remember before 180 pulse, 2 alpha and beta components of doublet correspond to 2 and alpha and beta components of carbon 13. H alpha, which was coming because of C alpha, now becomes C beta or H beta. Why? Because we are applying 180 pulse on carbon. Though we are interchanging, we are inverting the population. So H alpha is now because of C beta. Similarly, H beta is now because of C alpha. This is what we simply did the experiment by applying a 180 RF pulse. And what is the effect? The effect of this is we have changed the label of alpha and beta of proton. What was alpha became beta, what was beta earlier became alpha. The effect is we interchange the label of alpha and beta spin states of proton. That is what we did. What does it mean now? Earlier, when you apply only on 180 pulse and pass the proton, we inverted the population. They continue to move in the same direction. But now, simultaneously we are applying carbon 13 pulse, 180 pulse. H alpha became H beta became H alpha. That means fast moving H alpha became slow moving H beta, slow moving H beta became fast moving H alpha. Then they continue to move in the opposite direction. They move in the opposite direction now. As a consequence, what is going to happen? The proton spin components continue to move in the opposite direction for another tau delay. What is that another tau delay? We have applied 180 pulse in the middle of 1 hour 2J. So another tau delay is 1 hour 4J. So what is going to happen now? When they start moving, continue to move in the opposite direction, they instead of getting refocus, they continue to dephase. Okay? They continue to move in the opposite direction. If they were moving in the same direction, they would have refocused. They are moving in the opposite direction. So what is happening for the proton? By simultaneous application of the two 180 pulses on proton and carbon, we interchange the labels of proton and carbon. I mean, especially proton doublets, not carbon, proton doublets. Proton also, of course, 180 pulse inverted the population, but proton, which was coupled to H alpha coupled to C alpha, now became H beta coupled to C beta became H alpha. As a consequence, we interchange the labels of proton, okay, spin states, and they continue to move for another tau delay, which is equal to 1 over J, and they get refocused. Instead of getting refocused, they start moving at the opposite direction. They get continuously dephasing further. But you should also remember one thing. So far, the carbon 13 magnetization is still along Z axis. We have not touched anything. Only thing is we applied 180 pulse and inverted from plus Z to minus Z. That's all we did. Now let us say at E what is going to happen. At E, after the evolution for 1 over 2 4 JCH here, these H1 spin components acquire antiphase character. They are not, they have started moving in opposite direction, you know. So it will attain antiphase character. Now components are in the XY plane, remember. They have acquired antiphase character at point E. True, you know, in the previous example you saw here. They start moving and after exact half delay, this will come here, this will come here, or whatever it is. They come and become antiphase character like that. Okay. At F, what is going to happen? A pi by 2 proton pulse rotate XY component, proton pulse, moves H alpha component. Now because they are antiphase here, 180 pi pulse on this will rotate it. H alpha will go here, H beta comes here. This is what happens. It rotates XY component. H alpha moves to H, because they are all orthogonal to each other. We have been discussing from the class 1. H alpha component goes to Z, becomes Z, H beta goes to minus Z. The population states between 1 and 2 get interchanged. That is what we did by applying proton 180 pulse. Proton 90 pulse. The population between states 1 and 2 get interchanged due to 90 pulse on proton. This is what is happening now. Before 90 pulse on proton, this is 90 pulse on proton. What happened here? You will see the population between 1 and 2, they get 1, okay. Yeah, 2 was here, came down, and this 8, 10 was here, it went up. Okay. At F, what is going to happen finally here? The carbon 13 transitions have population difference of minus 6 and 10. The ratio of minus 3 to 5. That is what we know. When you apply simultaneously 180 pulse and also simultaneous 90 pulses, the magnetization is transferred from proton to carbon. It is minus into minus this 3 to plus 5 is the intensity ratio. This is what we are going to get. So, we got an antiphase character for carbon 13. Exactly what I said in the Inept, though I explained to you, this is all we require for getting Inept. This was added only to refocus chemical shifts. And then finally, like we discussed, by transferring the magnetization, there is a magnetization of carbon 13, 2 components, C alpha and C beta. There is the intensity of minus 3 and plus 5. This is what we saw when there is a transfer of polarization. That finally is going to happen at F. The carbon 13 have antiphase character transferred from proton and in the ratio of minus 3 to plus 5. At F, the carbon 13 90 pulse create antiphase transverse component that are detectable now. Here you are also applying 90 pulse on carbon 13 for detecting, and that will bring magnetization which was along Z axis to detectable along XY plane, X axis or Y axis. If you have a receiver here, it brings to Y axis. So, delta C equal to 5, delta C equal to minus, antiphase character, and here we can detect the signal. The component of the doublet are antiphase with intensity minus 3 and plus 5, like in the heteronuclear polarization transfer. And of course, this is what we have to do, we have to collect the signal. But here there are 2 things which you have to solve. If it is antiphase character, we can't do the decoupling. I told you. If we do the decoupling, whatever the intensity gain is lost. So far we understood how the magnetization is transferred, polarization from proton to carbon 13 by pulse sequences, and in between 2 180 pulses for refocusing, chemical shifts, etc. we discussed. But at the same time, you should also know there is the antiphase character. Decoupling is not possible. It is very difficult. It is possible, but you will lose the signal intensity, whatever the gain we got. We have to address that issue, one thing. And another issue is there is also natural abundance carbon signal coming. That also we have to suppress. If you do not suppress it, there is no polarization transfer won't be 100%. We will not be seeing the 100% transferred signal. So, we have to suppress the natural abundance carbon 13 signal, and also we have to convert the antiphase to in phase to go through the decoupling. This is what is important we do. So, in the next class I will discuss how we do this. Right now I am going to stop, but I told you what we did today. We discussed about the spin echo sequences and polarization transfer, especially polarization transfer, heteronuclear case. We understood there are 2 ways of doing polarization transfer, NOE and Inept. NOE do not need a J coupling, it is a through space direct transfer, whereas Inept requires a chemical bond. We saw that. And then how Inept transfer takes place from antiphase transfer to antiphase transfer, antiphase signal to antiphase signal. In proton, first we create antiphase signal by applying a pulse and giving a delay of 1 over J, 1 over 2 J, and then apply simultaneously on 90% on both of them. The magnetization jumps from proton to carbon 13, and carbon 13 will be antiphase. But there will be evolution of chemical shifts also. To avoid that, we apply 180 pulse in the middle, and we create a spin echo sequence in the middle of the TD, and then you are going to see what is going to happen. We get antiphase characters for the carbon 13. Finally, diagrammatically in different pulse sequences at different stages of the pulse sequence how it evolves, we understood. And we finally understood carbon 13 magnetization achieved because of polarization transfer is antiphase character with intensity -3 and +5. Also, there is a natural abundance signal coming because of that. That also we have to suppress. And antiphase has to be made in phase character. Only then we can do the decoupling. That already we know how we can do. Earlier example I showed you when we are trying to understand the spin lock. The spin echo. I told you that earlier. But anyway, so we will discuss how do you address these two issues in the inept sequence in the next class. Thank you very much.